Now the question is, we discussed scoring for match, mismatch, importance of scoring gaps. Now the bigger question is, how do we find the base alignment? One way is brute force approach. Generate the list of all possible alignment between two sequences and score them accordingly, or accordingly what we have discussed earlier, score for match, mismatch, and the gap, preferably a fine gap penalty. Choose the alignment with the base score. Yeah. Okay, straightforward and easy, but there are some issues. Let's look at the global alignment problem between two sequences of equal length n. And we'll realize that we have to compare this many possible alignments for the length n sequences. Just give you a number. This may not give you good feeling. In general, being a data scientist, but it's nice to give a number. So let's say I have two sequences of length 100 and I have to actually compare nearly 10 raised to 77 possible alignments. This is a huge alignment. Hence, using the brute force is not a good approach to solve this alignment problem. Either it is a global alignment or a local alignment problem. So can we find efficient algorithm? Can we find at least one efficient algorithm to align two sequences? That's going to be our efforts in next couple of slides. So what I'm going to do now is move away from the sequence alignment problem and try to look at some problem which many people are studying, which is called the Manhattan heuristic problem. So I'll take a detour from sequence alignment problem and I try to see that if there is a problem which is similar to sequence alignment problem, then I can use the solution of that particular problem to solve a sequence alignment problem. So what we are going to do is, we are trying to understand the Manhattan heuristic problem and see if I can formulate my sequence alignment problem as a Manhattan heuristic problem, and then whatever solution people have developed for Manhattan heuristic problem, I can apply to the sequence alignment problem. So what is Manhattan heuristic problem? So let's assume that we are tourists in the Manhattan, New York, and we have been put it here. So this is our starting point. This is where our hotel is, or end point, and this is a maze of roads where each of this circle is an attraction where we want to go, take some photo, selfie, put in Instagram. Okay, so as a tourist, we would like to see as much possible as we can. Okay? We want to visit many touristic places. But unfortunately, we can go only in one way. So once I start from here, I cannot go back. You can see these arrows. All these arrows indicate that once we travel in that particular lane, we cannot go back to that lane. In other words, I have to find a path which allows me to go from one place to other place and possibly touches as many attraction as possible. So Manhattan tourist problem is the tourist who is visiting Manhattan wants to visit as many as much possible the attractions. So, what is the route that we take in order to visit as many attractions as possible is the Manhattan problem. Is there any path exist? So, I have drawn here 3 paths. Route 1, which is very straightforward. I'll go straight on this line and then end in the my endpoint. When I travel on this road, you can see this is the route 1, this is route 1. I will touch upon 1, 2, 3, and 4 attractions. Okay. So let's see. So if I travel on the route 1, I will touch these 4 attractions. I can go to the 4 attraction, visit them, and end my journey. So score for route number 1 is 4. If I give each attraction a 1 as a score. So all attractions are equal, I'm assuming, and I'm giving them a 1 score. So I have traveled 1, 2, 3, and 4. So summation of all those 4 is equal to 4. Now let's look at route 2. Instead of trying upward, I'll go downward. Okay. So we are asking question, can we do better? So I'm looking at route number 2. I'll go this path, this path, this path, and this path. Okay. So here I have touched on this attraction, and this attraction. So my score is lesser than route 1 because I have 1 plus 1 plus 1 is equal to 3. And of course, we can do better. We can try to figure it out other routes. So what we'll do is we'll go to the route 3, which is little bit complex. So I'll start with here, I'll go here, I'll go here, I'll go here, 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 and here. So if I do this travel in route 3, I have 1, 2, 3, 4, 5, and 6. Correct? So I have now 6 attractions on this route and have visited all of them. This is more than any other route we have considered. It's better than route 1, route 2, and currently for us the best path through the city is route 3. There might be other better path which can go beyond 6. It is possible. And the question we are asking, can we actually find this path systematically? I have to go back and see whether there is a path which is better than 3. Currently, the best path through the city for us is 3. But to figure it out, I have to do the brute force approach, correct? And look at all possible paths between my start point and the end point and find out which is the path which allows me to go and travel more than 6 attractions. Or is there any path which can allow me to travel more than 6? So that question needs to be answered systematically rather than looking at all the unidirectional path in this particular Manhattan grid. So what we are going to do is, we are going to take each of these junction as a node and the road in between as an edge. You can see I can construct, correct? But I'm not going to do, or I'm not going to construct just edge, but directed edge. And also, what I'm going to do is, I'm going to provide this directed edge a weight if there is an attraction on that path. So, for example, here, if you go on this path, there is a weight of 1. If you want to go on this path, weight is 0. On this path is 0. This path is 1. Hence, I have actually provided a weight for my each edge. And similarly, I can construct a large graph. And that will be my new graph, where each of this starting and end point and the starting point for each of this road will be the node. Intermediate junction will be also node. The path connecting or road connecting this node to this node is considered as the edge. This is a directed edge because the here path is a unidirection, and I am assigning a weight of 1 when there is a of 1 to this particular edge when I travel through particular attraction. Here, when I travel to this particular road, this road, this road, this road, it is assigned 1. Similarly, this one, this one, this one, this one, assigned 1. So, all these edges has a 1 as a weight. Remaining edges where I have not, there is no, these are 0, these are 0, and these are 0, these are 0. Okay. So, this is a cyclic graph. And if you look at it, what I am trying to do is, I am trying to travel on this graph. This red path is my travel plan. And this travel should lead to me to as much point I can collect. So, when I travel in this graph, each time I am collecting some points, okay. So, I can actually note it down, these points on each of this route. So, let's example, if I travel from here to here, I am collecting 0, here to here 0, here to here 0, here to here 1. Remember, okay. Similarly, if I travel here to here, again 1 because here I am collecting 0, here I have 2 because I am collecting 1, and I keep going to do it, and then if I keep putting the score at the end, I will have score here equal to 3, 4. This is the path I am following, just for your information. Then fine, and okay, or I can follow the path which we have followed in the blue. 2, 3, 4, 4, 5, 5, 5, 5, 6, 6, 6, and 6. So, this is the path I am following. Okay, I can follow the blue path. So, 0, 0. Okay, that was a good one. Yeah. See, this one is the proper one. Okay, so what we are interested here in the Manhattan heuristic problem is finding a largest weighted path between the start and the end nodes. We are interested in finding a largest weighted path. This may be the largest weighted path, then we are interested in finding this path. And why we are interested in? Because if you look at the sequence alignment problem, it's an analogous problem to the Manhattan heuristic problem. And what we are going to do is, we are going to take sequence alignment problem and try to see whether we can project it to Manhattan heuristic problem. So let's take an example. I have a two sequence AT and GAT with alignment score of for the match equal to 1, mismatch is equal to -1 and gap is equal to -2. Currently I am using a constant gap score of -2. We can use a fine gap score or penalty also, but right now we are keeping this as a constant gap. So as we discussed, we want to create a graph. So what we are going to do is, we are going to create a nodes or set of nodes. So we have a AT and GAT. So I'm going to create a node. Let's say here this is of length 2 and this is of length 3. So I'm going to create nodes which are equal to length plus 1. So here this is node is equal to 3, and for this one 4. So I'm going to construct 3 cross 4 grid of node. So 1, 2, okay. Now the A and T I am putting here, G, A and T I am keeping here. Now I'll draw all the unidirectional arrows from each node to another node. Remember that in this particular case, we can actually have a diagonal route also, unlike the Manhattan heuristic problem, where in diagonal they have some building. Here it's empty, so it is allowed route. So diagonal is also allowed route in sequence alignment. That's the only difference. But these are acyclic. This is also a cyclic graph. Now, this particular alignment here, which we are looking for, I have constructed a graph which is similar to Manhattan heuristic problem. Only difference is there is a diagonal path, but it is still like Manhattan heuristic problem. It is a cyclic graph. There is no cycle in this graph. Now I have to decide what are the weight. So if I travel on this particular graph from this to this direction, and I will look at the G and T as my my two letters to be aligned, then if I travel this one, I am not at all considering A. So there will be a alignment pair here come as a weight. Similarly for this one and for this one. And in similar manner for each of these edge, I can provide an alignment pair. So this is more refined drawing. Okay. which is similar to this one. And now let me define how the alignment pair is constructed. What does it mean by alignment pair? So here I'll take this particular node, and there are three possibilities, and there are three kinds of arrows. If I travel on diagonal, I'm aligning J with A. When I'm traveling on this particular one, I'm aligning A with gap, and I'm traveling on this arrow, which is downward, J. I can keep doing for each of these arrows and provide them, as I told you, score. Now if I do that, now the interesting part here is it is now similar to Manhattan alignment, a touristic problem. If I do this, then this problem is similar to Manhattan touristic problem, where I have to start from the node 1, let's say, and reach to the node 12, correct? And find a path such that my score for that particular alignment is maximum. So let's look at different paths which I have created for this example and the score associated with them. So I have provided here several alignments. I started with this path. I took this one. So this is AG. I took this path, means that there is a gap with A. Then I took this path, which is T with gap, and then took again, so gap with T. So this is my alignment when I take this particular path, and the score for that is -7. Similarly, if I take this alignment or this path, I'll get gap, 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 align with G, A and T, and then gap, gap, AT, which is -10. So if I take this particular path, that's a poor path from starting to the end compared to the previous one. Now I took another path where I have a gap aligned with G, alignment with A with alignment with A, T aligned with T. So this is a path, and I got score of 0. Remember, -2 for gap, positive for match. Similarly, I can take a diagonal, and this one, the score is -4 because I mismatch, and the gap. Hence, you can see that if I compare all of this, this is the best alignment. Also, if we visually look at it, this is also best alignment we can do. Now, I have compared 4 paths, and there are much more paths here. I'll let you find it out as a homework, how many paths are there in this particular problem. But the question is how we can solve this particular problem, which is systematic, and also the algorithm which we are going to use to solve this problem should be efficient. And it happens that there are algorithms available in the literature which people have used to solve the Manhattan tourist problem. Here we have shown the best possible alignment by trying all other possibilities, but in general we want to know how do we arrive at the best alignment without having to try out every possible alignment. So Manhattan touristic problem in the literature has been solved using dynamic programming. Since we have shown that sequence alignment problem is analogous to the Manhattan tourist problem, we can solve this particular problem using dynamic programming also. So what is dynamic programming? It is an optimization technique, finding the best weighted path from this node to this node. It's an optimization problem. What it does, it breaks the problem, larger problem, into a simpler sub-problems, and such a manner that it solves the simple sub-problems in a recursive manner so that we yield a global solution. So what we are trying to do here is finding a local based solution which is also a part of a global solution. You can think that way, so that we can weed out some of the paths locally, and hence as we go recursively and update and try to find another local problem, we yield at the end the global solution without trying out all possible alignments. So next we are going to learn how to solve this problem numerically and efficiently. Thank you.